All right, let's dive into one of the weirdest, most foundational ideas in all of physics. We're talking about the truly bizarre, almost schizophrenic nature of light.
It really seems like a simple question, doesn't it? I mean, it should be one or the other. But as we're about to find out, the universe's answer to this question basically broke classical physics and blew the doors wide open for the quantum world we know today.
So what's the big deal here? Well, think about it like this. A particle, like a rock, is a solid thing. If you throw two rocks at each other, they're going to collide. But a wave, like a ripple in a pond, that's just a disturbance. Two ripples can pass right through one another and just keep on going. They seem like complete and total opposites. And this fundamental difference set the stage for a massive scientific showdown. I mean, this argument went on for centuries. The greatest minds in physics were totally split, each one digging in their heels, fiercely defending their idea of what light really was. In one corner, you had Team Particle, and their champion was the legend himself, Isaac Newton. He was absolutely convinced that light was made of these tiny, bullet-like things he called corpuscles. And in the other corner, you had Team Wave, led by guys like Christian Huygens and Thomas Young. They were just as sure that light was some kind of vibration, a wave moving through space. For the longest time, nobody could prove who was right. It was a total stalemate. But then, it was time for round one. In 1801, a brilliant scientist from Team Wave, Thomas Young, came up with an experiment so clever and so powerful, it's still blowing minds in physics classes today. And the setup is actually beautifully simple. All you do is you take a beam of light, you shine it at a wall that has two very thin parallel slits in it, and then you just look at the pattern it makes on a screen behind that wall. That's it. Now, here's where it gets really interesting, because this simple setup leads to two totally different predictions. If Newton was right and light is just a stream of tiny particles, you'd expect to see two bright lines on the screen, right? Just like if you sprayed paint through a stencil. But if light is a wave, something much, much weirder should happen. The waves would ripple through both slits at once and then interfere with each other on the other side, creating this complex pattern of many bright and dark stripes.
So, what did Young actually see on the screen? Bam! An interference pattern. Not two lines, dozens of bright and dark stripes. There was no denying it. This was classic wave behavior, plain and simple. It was a knockout punch for Team Wave.
So that was it, right? The great debate was finally over. Light is a wave. Newton, the giant of science, was wrong. And for about 100 years, that was that. It was settled science. Case closed. But it turns out the universe had a major plot twist in store for everyone. Flash forward a century. A young Albert Einstein is puzzling over a completely different phenomenon, something that the whole light is a wave theory just couldn't explain at all. He was about to reopen the case in a huge, huge way. This new mystery was called the photoelectric effect. And what it is that scientists found that if you shine light on certain metals, it can literally knock electrons right off the surface. This creates an electric current. It's the basic idea behind every solar panel out there. But here's the part that made absolutely no sense. If you used a really dim blue light, electrons would pop off that metal instantly. But if you used an incredibly bright, super intense red light, nothing. Not a single electron moved. Now, if light is a wave, this is just impossible. A bigger, brighter wave should have way more energy than a small, dim one. I mean, a tsunami should do more damage than a little ripple, right? Einstein's solution to this was revolutionary. He said, what if light isn't a continuous wave at all? What if instead it comes in these little individual packets of energy? And he gave these packets a name, photons. And here was the kicker. The color of the light determines the energy of each individual photon packet. Blue photons have a ton of energy. They deliver a really hard punch. Red photons, on the other hand, are low energy. They're more like a soft tap. So it doesn't matter how many billions of soft red taps you hit an electron with, if no single tap is hard enough to knock it loose, nothing's gonna happen. It was all about the quality of the punch, not the quantity. All of a sudden, light was acting like a particle again. So now what? We're at a complete impasse. The score is tied. The double-slit experiment proves without a doubt that light is a wave, but the photoelectric effect proves just as clearly that light is a particle. Both experiments are correct. You can do them right now and get the same results. So who wins this fight? How can both possibly be true?
Which brings us right back to where we started. After this whole 300-year-long brawl, what's the final answer? Is light a wave, or is it a particle?
And the answer is one of the most mind-bending and honestly poetic ideas in all of science. Light is both. The best way to say it is this: it travels like a ripple, but it lands like a bullet. It has the properties of a wave and a particle, and which one you see just depends on how you look at it.
What physicists call this today is a probability wave. So when a photon is just traveling through space, it's not really in any single place. It's spread out like a wave of possibilities. But the very instant it interacts with something, like hitting a screen or an electron, that whole wave of possibilities collapses into a single point, and it lands like a particle. Now, I know this might sound like some weird philosophical trick, but I promise you it's not. This strange dual identity of light is absolutely fundamental to the technology that powers pretty much everything in our modern world.
We actually take advantage of this split personality all the time. Engineers use its predictable, dependable wave nature to design things like lasers and fiber optic cables that carry the internet. And they use its distinct particle nature to build things like solar panels and the sensors inside every single digital camera on the planet.
It's really not an exaggeration to say that we need both sides of light's personality. If light had just decided to be a simple particle or just a simple wave, the technological world that we live in today would be completely impossible.
And that just leaves you with this incredible final thought, doesn't it? What light teaches us is that reality isn't always a simple this or that. It can be both. It literally behaves differently depending on how we choose to observe it. It really makes you wonder, what other fundamental truths about our universe are we completely missing just because we aren't looking at them in the right way?